And you see the presentation up, correct?
Yes.
So for those already here, welcome. We are a few minutes early. If you're new to this, what you can expect is that um, I'll give it about 2 minutes at the top of the hour for people to roll in, because from past experience, we have people continuing to roll in the first 1 or 2 minutes or so. But then we'll get started. Okay, let's see here. For everyone already here, welcome. We still have 2 minutes to the top of the hour, according to my computer. And then we'll give it another about 2 minutes as for people to roll in, and then we'll get started. Alexis, did something change? Because I don't hear the beeping as people come in.
Yeah, it's the update. They updated Teams, so it's silent now.
Oh yeah, that's actually good. That's actually good. It's always a little bit annoying. So based on that, I think I'll just give it 1 minute after the hour, and then we'll get started. Okay, it is the top of the hour. So for those already here, welcome. I'm going to give it one more minute because I see people rolling in. But those of you that were hearing me and Alexis, Alexis, by the way, is our marketing coordinator, and she helps me get this set up, keeps me straight. Before, when people would join Teams, you would always hear this beep, and it was very distracting for the speaker. But now that doesn't happen anymore. So it's 11:01 according to my clock. So as soon as it changes over to 11:02, I'm going to go ahead and get started. So we'll save a minute today. And don't worry, I'll find a way to make up that minute at the end. I'll have something to add. Yeah, people still coming in. Okay, we'll get started. So welcome. I'm Mike Riddle, and this is one of our ongoing webinars on topics related to fiber optics and fiber optic cable. And today we're going to be talking about ADSS sag and tension calculations. So first up, this is an RCEP compliant presentation. So that means that we've met the standards and requirements of the Registered Continuing Education Program. And so at the completion of this, you can get 1 hour of RCEP continuing education credit if you want. And I'll tell you at the end how to do that, but it's pretty simple. However, this just means that we've met their standards. It does not mean that they approve or otherwise endorse any of the content today. So our purpose statement. So today we're going to talk about how to get the sag and tension data that you need for your product. And we're going to see that there are 3 methods of obtaining that. There's tabulated data, and we're going to look at how that's done and what that means and what's all there and all that kind of stuff. We're going to show you how you can generate your own using this program that we have called ACES CATS. And we're also going to talk about how you can generate your own using PLS CAD or SAG10 as well. Specific learning objection is understanding those 3 methods. Along the way, we're going to learn about such things as maximum rated cable load and zero fiber strain margin and how they are important to the sag and tension data that you get or generate yourself. We're going to talk about some implicit assumptions that go into these calculations. We're going to talk about the difference between mechanically independent and mechanically coupled spans. And then we're going to talk about when it would be better to use the ruling span concept versus a simplified method that we're going to initially show here. So the agenda, this is the introduction. We've already talked about the course description and the learning objectives. So next up is the presentation itself. It'll last, I hope, about 15 minutes. And then questions and answers. So please keep the questions to the topic at hand. We will at least try to unmute your mic so you can verbally ask questions, but for some reason that doesn't work, because sometimes it doesn't seem to work, you can still type questions in by chat. So we'll figure it out at the end if you got questions. So let's get going. So I want to start off today with 3 observations. So first, I have heard over the years people tell me that snow and ice doesn't accumulate on ADSS in the field. So if somebody says that to you, you can take this picture and show it to them, because I only have to provide one picture showing that that's not the case. to illustrate that, or to demonstrate that that is in fact not the case. And this is one picture. I have others if somebody wanted to dispute this. So in this case, this is an ADSS cable, and you see it has significant amount of snow or ice accumulated on it. It's just a myth that ADSS does not accumulate snow and ice. Uh, Somebody a long time ago said that because it was plastic and it would be flexing, that it would act like those old-fashioned ice cube trays in your freezer. And no, it does not. And you can understand that because of the nature of the materials used to make ADSS, it's a little bit stretchy. So under snow and ice, it will sag significantly. So the vertical sag under ice loading could cause you to exceed ground clearance for code clearance, and that's a bad thing. So therefore, you do need to check it. It's also interesting, just before I move on, about this picture. This line appears to have a second ADSS on it, and it's interesting that it does not have snow and ice on it. So maybe it did shed after a while, but it didn't. It it did accumulate at least at one point on this one cable. So the observation number two, wind conditions are also important for ADSS. As I mentioned before, the nature of its materials are such that the cable is light and elastic. I used the highly technical term stretchy before. So consequently, under wind, horizontal blowout can be significant, and it too must be checked. And then there's a third thing. You probably already thought about the first two, but there is a third thing that you might not have thought about. What does that stretchiness or elasticity mean for the fiber that's in the cable? Well, because it's stretchy, you could end up putting stress on the fiber, and that's not a good thing. We'll talk about that later in more detail. So you have to use the strength in the cable in order to control fiber strain, and we'll talk about how to do that as we go through this presentation. And here it is right here. What is fiber strain? Fiber strain is the tension on the fiber. Now, optical fiber is strong. The standard proof test for single mode fiber is 100 kpsi, but it's glass, so it's brittle. So it becomes a good idea to keep tension off the fiber. It enhances the long-term optical reliability. The simple way of putting it is no strain means no fibers. And again, because of the brittleness, that makes it vulnerable to cyclical loading effects. So you load it and you unload it, you load it and you unload it, can have a bad outcome on things that are brittle. So we'll go ahead and define this term here, that the fiber strain margin is the difference between the tension on the cable and the tension on the fiber. And the zero fiber strain margin specifically is the point at which the optical fibers begin to experience tension. We'll see later that that's typically expressed in terms of percent rated breaking strength of the cable. But with ADSS, we often just use the value itself and not the percent rated breaking strength of the cable. We'll see that later as we go through. As a general rule, the higher this value, the better. And I do discuss fiber strain in extensive detail in a separate webinar called Understanding the Loose Tube Design Concept. Today, it's just kind of an overview of the topic. So as I already talked about, to properly check clearances, both vertical and horizontal, you need to factor in ice and wind loading. Industry practice with ADSS has been to have installation or every day, meaning no ice, no wind, sag at 1% of span or 1.5% of span. Now, in theory, it could be more, it could be less, it could be somewhere in between. But these are the two most common values that you see, 1% or 1.5%. So it's as simple as this example. If I had a 300-foot span and I'm allowing 1.5% of sag, the sag would be 4.5 feet or 1.4 meters. If I decided I wanted only 1%, it would be 3 feet, a little under 1 meter. Now, recently, in recent years, I have seen some customers and some competitors use 0.75 and even 0.5. I consider that risky because that increased tension can do, sorry, I hit the wrong button. Risky in my opinion because the increased tension can lead to jacket tears or cause alien vibration problems. I just don't think it's a good idea. So we talked about those three observations. Now let's try to connect them. We want to minimize the fiber strain on the cable. And that's another way of saying, let's maximize the zero fiber strain margin of the cable. So the best practice in cable design is to have no fiber strain, not just at everyday condition, but also at the maximum condition. And with ADSS, we use the term maximum rated cable load. And I'll show you more about that in a minute. This is our design standard, but sometimes it's not practical. So there are acceptable alternatives, and those alternatives are not having strain at everyday condition, but allowing some strain at that maximum tension the cable will experience. 0.2% is I characterize it here as good because the ideal is 0, but good is 0.2% fiber strain. This is a conservative limit. It's derived from Corning research. It's talked about in that other webinar I mentioned on a previous slide. If you keep fiber strain static at this level, you should have an expected life of 40 years. Just the way the expected life is a probability type calculation. So it's not a guarantee. You might get more, but you could get less. But if you were betting, you would bet on getting 40 years. You could say that because fiber optic cable like ADSS is not under tension under an everyday condition, right? We want the zero fiber strain margin to be above the everyday tension, whether we're in this next best option situation or in the best practice or the ideal practice. So every day it's not experiencing strain. It's only under wind and ice conditions such that you have gotten to this MRCL level that the fiber would have strain. So you can make an argument that if you're only wanting your ADSS to cable to last maybe 20 or 25 years, and many utilities do, that you could allow a little bit more strain and take that little extra risk. And if you take that approach, you could say 0.3% would be acceptable. Now, the next level, which I think is risky, bordering on crazy, is 0.4% strain. Fiber will fail very quickly at this level of strain. Again, somebody doing this is taking the chance that the cable would not be experiencing this for very long, but the failure rate at 0.4% is like on the order of hours before the fiber is likely, again, an expected value to likely to fail. Now, every cable supplier has some design policy on their fiber strain, but often you have to ask what it is. And so if you are a user, you should be interested in this to understand what they're doing. And I'll show you that later. how you can understand what they're doing and know what to ask. So I've talked about this term MRCL already, maximum rated cable load. Now, for some reason in the IEEE, they've chosen to use the term MRCL for ADSS, but the term that they use for OPGW is maximum rated design tension. They mean the same thing. They're just talking about the tension that the cable should never ever exceed under any design loading condition. So whether it's a standard NESC condition or you want to throw 2 inches of ice and 100-mile-an-hour wind at it, whatever, you don't want the cable to ever exceed that. It is not the same as the rated breaking strength of a cable. And for ADSS, typically MRCL is about half of whatever the RBS of the cable is. So you can think of it as that's the useful strength of the cable. You can't plan on using the full rated breaking strength of the cable. You can only use up to MRCL. So that's all some background information. Let's explore how you get the sag and tension data that you need. Step 1 is determine your loading criteria. Step 2, get the actual cable specifications. And then step 3, get or generate the data. 3 easy steps. So step 1, get your loading criteria. So you've probably got some base loading criteria. If you're here in the United States, it's your NESC Rule 250B loading zones are your starting point. Now, you're a utility or on a specific project, you might have additional criteria to add, maybe a maximum tension that you don't want to exceed, maybe a maximum sag that you don't want to exceed. And it's possible, don't see this a whole lot with ADSS, do see it quite a lot with OPGW, but you might have extreme ice or concurrent wind and ice conditions per the NESC rule 250C or D, or some additional criteria, beyond the standard NESC rules. Or likewise, if you're not in the United States, I'm sure your country has some standard criteria that you use, and maybe something that goes beyond the standard criteria. So next up is get the cable specifications. So you're looking for a cable data sheet, and you're looking for some key information on that cable data sheet. The key information that you need are these 6 pieces of information. The outside diameter, no surprise. The unit weight, no surprise. Maximum rated cable load, we've already talked about that. You need to know that. Cable modulus. Now, we're going to see some variation there, and you're going to want to know what to use. And so we'll talk about that later. You're going to need a linear expansion coefficient, and you're going to need a strain limit, really the zero fiber strain margin. And as I mentioned earlier, these are going to be found on the manufacturer's cable data sheet, or if you have to, go ask them for the information. So what I'm going to do now is go through the data sheets of 4 well-known suppliers, and I'm including some of my competitors, and I'm trying to be fair to them about this. All right, but we're going to look at how everybody presents the data in slightly different ways. So first up is my company. So here's a typical data sheet for us. Cable diameter, cable weight, maximum rated design tension. So when I had our technical team put together our data sheets, I used the OPGW term. So we are in the process, we're going to change this to MRCL because I checked the standard and saw that, oh yeah, they actually used the different term even in the standard itself. So, okay, we'll fix that. Zero fiber strain margin is given. So to illustrate my current previous points, you'll also see the rated breaking strength, and you'll notice that I don't consider it terribly important to getting these calculations done. So the rated breaking strength of this cable, 4,000, let's call it 500 pounds. The zero fiber strain margin is, let's call it 2,400 pounds. So until you have 2,400 pounds of tension on this cable, the fibers are not seeing any strain. And then at the maximum rated design tension, let's call it 2,900 pounds. So 2,900 pounds is the maximum amount of strength that you can use in this cable. And note on this cable, I said earlier, we prefer to have zero fiber strain margin and MRCL be the same, but here's an example of a cable where that didn't happen. So you got what, 500-pound difference between the MRCL and the zero fiber strain margin point. Actually, I just realized we didn't show it. We should have showed that the strain here would be 0.2%. So for us, if it's not zero, it's that 0.2% level that I mentioned earlier. Here's the modulus of elasticity. Notice initial. There's also a value for final and creep. We're going to talk about these later, but notice that this initial one is the one I say to use. And as I say, we'll talk about modulus later. And then the coefficient of thermal expansion is down here as well. So you got everything you need. Next up is Prismium. So their data sheet, you find the cable diameter, you find the cable weight, maximum rated cable load, MRCL, initial modulus, the coefficient of thermal expansion, and you've got this long-term limit. So a couple things to point out about theirs. So the long-term, this is really their fiber strain margin. They are not showing the zero fiber strain margin directly, but it is factored into their sag and tension data. And we're going to see this later in the presentation. And the other thing I want to point out here is notice that they gave 3 values of modulus like NCAB did, but the initial and the final are the same and the 10-year is different. So I say down here, initial equals final equals not really. This is a simplification that's okay in the distribution world, and I'll talk about why later. For now, just kind of accept it as being okay. Next up, OFS. We got cable diameter, cable weight, the short-term tension. So they're using that as maximum rated cable load, short-term. Why? Because, you know, the cable might be at MRCL on the order of hours, you know, when there's wind and ice loading present. Long-term is your zero fiber strain margin, or kind of close to that. I'm taking it that way, but strictly speaking, it actually doesn't tell you about the fiber strain or the zero fiber strain margin. I'm just guessing that they would, that this is also the value at which there's no, or that the fibers first begin to experience a strain. So where was I? Cable modulus. So here they give just one value. Again, we'll talk about modulus later. Linear expansion coefficient, so they have that there, and this estimated breaking load is rated breaking strength with a different name. Okay, let's keep going. Next up, AFL, approximate cable diameter, they got that. They got the cable weight, the MRCL, cable modulus. Now notice again, they give initial, 10-year, and final, and they give 3 values. Not 2, not 1, but 3. Coefficient of linear expansion. The fiber strain margin is not provided, and they don't give an everyday or long-term limit. So that's missing information. I think you should ask them for that, and they ought to be able to quickly and gladly provide it to you. And I did make a good faith effort on their data sheet to find it somewhere, and it wasn't there. Just saying. All right, so now step 3, get the data or generate the data. So you got 3 sources. Manufacturers provide tabulated data. Generally, this is limited to the standard NESC loading conditions, but they can run it for whatever conditions you need or want. Second way you can get the data is to generate it yourself. This is a program that we have, but it can be used for any supplier's cable, and I'll show you how later. Or you can use PLS CAD or Southwire SAG-10 program. We'll talk briefly about PLS CAD at the end of the presentation. So here's the tabulated data that you get. So first up, we're going to go by the 4 suppliers we talked about earlier. First up is us. They all have, like, there's header information. It gives you the same values that we were just talking about. Plus, you'll see what loading conditions were used. So cable specs, MRCL, the 0 fiber strain margin point, all that kind of stuff. So then here's our actual tabulated data. So this is the everyday condition, no wind, no load, no ice. Notice that it's, for this cable, when this data was generated, it was set at 1.5% span for the sag. Here it is under the loading conditions. The previous loading conditions were NESC heavy. So here's your sag separated as horizontal sag and vertical sag. Okay. Next up, Prismian, the header information. Again, the loading cable information is echoed, and then the loading conditions are shown. In this case, NESC medium. Now, I said before on the cable data, they didn't give you information about the fiber strain, but on this sag and tension data that they provide, they do show this thing safe strain. And you could ask them, what does that mean? And what I figured out is what it means is it's 0 at every day, which is earlier is what I said you wanted, and they're allowing 0.2% at MRCL. So that's safe. I don't disagree with that in concept. They also offer 0 strain. You'll see that on some of their data sheets, and that means the fiber strain is 0 at every day and 0 at MRCL. And recall, I said earlier in the presentation, that's ideal. Not always practical, but it remains ideal when you can do it. Here's their actual data. Again, you see data for the everyday type condition, also set at 1.5% sag, and then under loading conditions. And you'll notice vertical sag, horizontal sag. It's also interesting that they give the ice only vertical sag. And incidentally, when you separate the sag vertical and horizontal like that, you make it very easy to check your clearances vertically and horizontally. That's why they do it. That's why we do it, for the same reason. They also actually give you the angle that the cable is at, which is interesting. OFS, again, the header information. Now, in this case, they say user defined. So you'll notice that there's no ice. There is a significant wind above 90 miles an hour. And you see the other information that's used here. So this is not a standard NESC loading condition. You see they do this short-term tension limit, which is really MRCL under a different name. And then they give a long-term. Um, this does not necessarily mean that it's the zero fiber strain margin point, but that would be a good guess. And then you have the other cable information down here. And then here's the data itself. Again, the everyday condition. Notice that in this case, they set it to 1%. And then here's the data under loaded condition. And then recall here, the wind speed was 93 miles an hour, 150 kilometers an hour. So notice how much blowout there is. It's quite a lot. The cable is almost, 84 degrees. It's almost vertical, completely horizontal at that wind speed. Okay. Next up, AFL. So again, they echo the cable specs on their header. But as I pointed out before, you don't have a maximum every day or your zero fiber strain margin. You should ask. And here's their data. Now, they present their data a little bit different than everybody else. They give it by individual span. So in this case, this is the data for a 400-foot span. What this does is it's allowing them, in this case, they're showing just the NESC light conditions, but they could have been showing some separate ice or wind condition as well. So it allows them to potentially show multiple loading conditions on just one data sheet. It's not bad. It's not good. It's just different. Okay. But again, the data vertical and horizontal. Okay. All right. So that was an overview of the different data sheets, how the different suppliers do it, and now you know what to look for. So what it means. So if something's not there, go ask. It's that simple. But you can also generate your own data. And my thinking is that allows you, you need the data. If you have to ask for the data, you got to go to somebody and ask them and write an email and maybe you get it tomorrow. But, if you want the data now, you can just do it yourself. And this also helps you to do what if analysis very quickly. And fast, easy, and fun, but obviously I work too much with fiber optic cables. And you can use this for any supplier's cable. You just need the basic cable data. So we'll show that. So how are we doing on time? We're doing good on time. So what I'm going to do is actually show it to you. If I can bring that up. Yeah, here we go. So the way you use it is you just go to our website, you click on this configurator, and then you'll see, well, what am I doing here? I'll just do it. So click here. Aces Cats. There is a login registration. It's just, we ask for an email. And we don't sell your data or do anything else with it. And if you don't want to get on our mailing list, you just let us know. So there's a quick sign in. I've already signed in, so it just brings me to the program. So here's how it works. So you put in your project information, which I can't type today, Mike's project, Mike's cable, whatever information. You can put the data in metric or customary units, and it will convert the other. So for the data, what I'll do, I just pulled up a cable, one of the first cable of ours that I found. Okay. Cable diameter 0.51. I'll do it in English units for the most part. Maybe I'll mix them just for fun. So cable diameter 0.51, cable weight 137.4, 0.51, 137.4. Cable modulus. So we're going to pick the initial, so 5.81. Coefficient of thermal expansion, 12.33. Maximum rated design tension, got to get that fixed too. Maximum rated design tension, 7. And maximum, we call it maximum everyday tension here for some reason, but that's basically 0 fiber strain margin. Naturally, I picked an old data sheet that doesn't show it as 0 fiber strain margin, but gives it as installation tension. That was the way we did it then. 1.75. Okay. Loading condition, what are we feeling like today? We'll just stick with medium, but you can fill in your own values. You can put whatever you want to here. And let's say that we want to be different today and we use 1.3% of sag, of span rather. We'll stick with 20C, why not? Okay. You've got your data now. And basically it's saying that the tension is exceeding the 0 fiber strain margin if the span goes above 400 feet on this cable. So it's giving you a warning. You can convert it to metric if that's what you want. If you want to go back and change something, what do we want to change? Let's change 4-pound wind is not enough. Let's make it 6. Okay, it's limiting my span. What I can do is I can allow more sag. Let's go to the 1.5% and calculate again. That didn't help. Let's just go to 2% sag. Yeah, look, now I can go to 200 meters or 650 feet. You get the idea. I mean, some of what I just did a little bit silly, but you get the idea. You can play and have fun. And if you want to start over, just hit new calculation. You can download your results and you can save the results and refer to them later. So upload them later. I had done some projects before. That's to save it. You can save your results. I've done some projects before. I could bring that data in and calculate that. So easy peasy. All right, all right. So I'm just going to flash through these slides. I really intended them as kind of like a reference. So if you want to get the slides and you want to go do this, this is going to show you step by step what to do. But you can see it's basically put in the cable data, pick your loading conditions or enter them, and then hit calculate. Okay, now, there are some people here who've been thinking about this. They're very experienced, very knowledgeable people. I'm thinking of you, Joe Ronaldo, and Tufuk. You're probably thinking, this isn't right. Only using an initial value of modulus? What's wrong with you, Mike? Well, using an initial value of modulus only implies that the ADSS is perfectly elastic and that there is no difference between the initial and final modulus and no creep. And we know that is not the case. And we further know that from the fact that 3 of the 4 manufacturers gave different modulus values, at least 2 and sometimes 3. So it's not quite right. It's a simplification. There's another simplification that's involved too, and that's that effectively this way of doing sag and tension calculations are treating spans individually. And what that means is it's as if every span was double dead-ended. And that's only true if each span is strung and clipped individually. You get this mechanically independent spans, which I'll illustrate in a moment. And this is done if you're using what's known as the moving reel installation method, and if you're using a trunnion type support clamp. So again, it's just easier to now show you on the next slide. So in the moving reel method, you load a reel on the back of a trailer or something, and you go to this structure and you bring it up and you dead end it. Then you drive your truck to this structure and you hoist it up and you put it in this trunnion type support, which would look something like this or this typically. Then you keep driving your truck and you hoist it up and you put it in another trunnion clamp and you keep driving until you get to the end of your line segment where you dead end it. So each of these spans or each of these is a fixed point, which means each span acts completely independent from all of the others. So this is what I'm calling mechanically independent spans. So uh, the other possibility is if you're using what's called the controlled tension stringing method, where you use a tensioner and a pulling line. And if you're using any type of suspension clamps instead of those trunnion type support clamps that I just showed, you get mechanically coupled spans. So that means the spans influence each other. And if that's the case, you have to use the ruling span concept, which would govern, hit the wrong button, which would govern, or better govern how the cables are going to interact with or how the different spans are going to interact with each other. What's going to happen is that the tension is going to equalize across all of the spans, and that's going to end up with the sag being greatest in the longer spans. So it's effectively a kind of a weighted average of the spans as opposed to just an average of the spans. We'll show you the formula in a minute. So I told you how to get all this data, and now I've said effectively, is it wrong? So do we just waste all of our time here? No, hold that thought for a minute. I'm gonna salvage the situation in a minute. Trust me. So again, here was the mechanically independent spans. Everything is fixed. Now here's the mechanically coupled spans. So you've got suspension clamps like this, or maybe like this, or maybe others. And these types of clamps, they swing or articulate, that's the fancy word, just a little bit. And it only takes a little bit to make a major change in tension and help equalize the tension between this span and between this span and this span. In contrast, up here, this span can be whatever. It's fixed here and it's fixed here. And this span can be whatever because it's fixed here and fixed here, and so forth and so on. It's a big difference. Oh, and then to talk about the control tension, and the way you're installing the cable there is you have a cable reel, say here, and you use a puller, and you have a pulling line, and you pull the cable in from one side to the other. So, was it all a waste? No. It just means that you need to understand the limitations of the methodology that we have used so far. It's fine for short to medium spans in a distribution environment. The theoretical error is acceptable. Now, a bold assertion there. How do I know that? Well, from experience. There have been no problems in reality. We don't have cables falling down all around the country every day and things hitting them and whatnot. Those things do happen. Cables do fail. Things do run into them. In my, I did a presentation on field problems, and I have a picture of a dump truck that's hit an ADSS cable, but not because of the error in the sag. Is my point here. This error um, uh, um, isn't causing problems in reality in the field. Now, for ADSS, the change in sag between the installation conditions, which are governed by the initial module of the cable, and the tension and sag that you're going to get in the final condition, which would be at the final or the creep modulus, it's much lower than for a metal cable. So the change in modulus over time or with field conditions for an ADSS cable is significantly lower than it is for a metal cable. It's specifically about half. And then again, the context here, short and medium spans, there are sagging inaccuracy in the field. If you watch how people in the real world install cable, the error that goes into sagging in the field outweighs the theoretical error. That's my assertion to you. So we can consider the method that we've presented thus far a simplified sag and tension solution. It works. Just understand that it has limitations. So in turn, that then leads to two questions. When it is appropriate to use this so-called simplified solution, because I use the terms short and medium, those are very subjective terms. So I would say 500 to 600 feet, so around 150 to 200 meters under the standard NESC loading conditions or whatever, something similar outside the United States. So if you're using the 90-mile-an-hour wind, I probably would not use this simplified solution. But if the spans are short, yeah, I'm back to, yeah, maybe it's okay. So basically, when ADSS is used on distribution circuits, I think this method is, for the most part, appropriate. I say for the most part, maybe there's some exceptions. Again, extreme wind or extreme ice conditions. Excuse me for a moment. There is a certain amount of judgment in deciding when you're going outside the bounds of when this method is appropriate. Which then leads to the question, when is it not appropriate? And when do I need to use that ruling span concept? Well, if you're using PLS CAD or SAG10, yeah, you're back to, you need to use the ruling span concept because that's the way these programs are based. And remember, these are the third source of sag and tension data. So if you're using PLS CAD, whether it's for a distribution circuit or a transmission line, well, yeah, then you can't use this method. You really need to use the ruling span concept. So what is that ruling span concept? Well, mathematically, this is the formula for it. And in words, what it means is it's the square root of the sum of the spans cubed. The spans cubed, so span 1 cubed plus span 2 cubed, and so forth and so on, divided by the sum of the spans. And then you're taking the square root of the whole thing. So as I said earlier, it's effectively a weighted average that leans towards the longer spans. You can calculate it easily in Excel if you just have a list of the spans and their individual lengths. And PLS CAD also does it for you, part of the built into the program. So let's give an example, simple line with just 4 spans. Here are the lengths. If you do the calculation, the ruling span is 220.4 feet or 67.2 meters. If you did calculated the average span, you'd see that the error is about 1%. Okay. So back to PLS CAD. If you're going, yeah, if you're going to use PLS CAD, then you need to know how to do a wire file. Well, I say you need to. It's a good idea to know how to do a wire file. You just should understand what's going on behind it. However, it's a lot easier to ask the cable manufacturer to send you one or to look it up in their library of wire files. I'm going to talk about it very quickly in the interest of time. It's not for the faint of heart to edit these wire files yourself. So please, if you choose to do this, proceed with care. To do it, you need to find the wire file. You use the open with and select Notepad. It's a text file, so Notepad works best. And then save it under a new name when you've made the changes. Then load it into PLS CAD and generate your data. So it's that simple. It's best to start with an existing one, what I call a donor file, and then edit the data. So this is an example. I'm not going to talk about this in extreme detail in the interest of time, but you could refer to this slide to see what's there and what it all means. Basically, you're editing the data that's in blue or circled in blue. The cross-sectional area, diameter, weight, rated tensile strength. No surprise to you. But do note that PLS CAD works off the rated tensile strength. That's not the same as MRCL. You have to manually check that later. There's a bunch of things in these files that you should not mess with. Don't mess with any of this, and don't change anything below this line. All of this. It's just stuff that's required by the program to run correctly and generate ADSS data. Leave it alone. Just change the basic information. Now, I've talked about MRCL and I said it's critical, and so is zero fiber strain margin. So you need to manually check that, right? Because if the program gives the tension that's above MRCL, you're risking long-term optical problems. Well, for that matter, short term or both. And if that happens, you're looking at dealing with that on your own. Any manufacturer who finds out that you exceeded the MRCL is going to say the warranty is void. So, and remember, the tension under any and all conditions must never, ever exceed the MRCL. And you need to check the zero fiber strain margin as well. So, recap. So now you know how to obtain your basic sag and tension data for your cable. You understand the meaning and importance of zero fiber strain margin and MRCL. You understand the difference between mechanically coupled and mechanically independent spans and how that's important to doing these calculations. You understand the difference between the simplified sag and tension calculations and those made using the ruling span concept, and you have a good idea of when each method is appropriate, and you know how to do your own ADSS sag and tension calculations. So, um, this is a first for me on these webinars. I am today assigning homework. So I'm asking that you go take a test run of the ACES CATS program. I showed you already how to get to it. And I ask that you go talk to another ADSS supplier and get their data and do the things that we talked about. Identify the key data, find the zero fiber strain margin, ask if you have to, identify the MRCL, and identify the strain at MRCL. Again, ask them if needed. And then as a bonus, run your own sag and tension calculations using PLS CAD or SAG-10. Now I'm gonna, since I've assigned homework, I'm gonna maintain kind of office hours to help if you run into problems trying to do this, but this will greatly reinforce your learning. So I'm available to help, just drop me an email or give me a call. All right, and thank you. So we'll open it up now for questions, either through the chat or if Alexis can unmute mics, you could like raise your hand, we'll unmute your mic or, okay, let's see. For some reason, I'm having a hard time scrolling to the first question. I'll get there in a minute. Uh, let's see. Okay, OFS long-term. I believe long-term is the max installation tension for the sag that is given and the region load. Yeah, it could be. Might be right. No stress strain curve coefficients are required as it is required for standard aluminum conductor. I assume that question is in the context of, well, maybe both. I took it initially as in the context of how PLS CAD is doing it. And remember, there are lots of things that I said in the wire file that are there to make it work for ADSS. And I trust that the folks at Powerline System have worked that out so that it's reasonably accurate. But yes, you don't need stress strain coefficients in PLS CAD. Now, I suppose you could go do a stress strain test and put them in the program like you would for a metal cable, I suppose, but I don't know what would happen. And I don't know if that would increase the accuracy or perhaps make it worse. I'm not sure. I find it a little bit complicated how they've adapted the program for ADSS. And I have to tell you, I don't fully understand how they've done it. I just take their word for it. And then for the simplified method, no, you do not need it. You're working off that initial modulus only. Okay. Question, are you going to share the presentation with us? Yes, that's a standard feature for us. So in fact, I'll go ahead and digress for a moment. If you want to get the continuing education credits, what will happen is everybody after this will receive an email as a follow-up. So if you attended today, you'll get an email. The email has three things in it. A link to the presentation. So that's how you can get the actual slides. You can also find a recording of it. You can't find something on Netflix to watch tonight, you could re-watch this presentation. Share it with your friends and family too, for that matter. Second thing in there is a link to take a quiz. So if you want the continuing education credits, you go click on the link and take the quiz. It's simple, 10 questions. You have to get 70% to pass, and then you get your 1 hour continuing education credit. This test is a little bit different. There are 3 questions that are actually optional because they're in the category of my homework there. It's asking you to actually do things that may not be practical for you, so you can opt out of them if you want. I don't like that, but I would be tough, but I'm told that I should not be tough on this case. The third thing that's there is a link to a survey. So give us some feedback to include, ideas for other topics that you'd like to be discussed, but all kinds of feedback. If you think, that's completely wrong, Mike Riddle, I'm always open to learning new things. If you think I'm wrong, make your case. So again, you can get the presentation by following the link in that follow-up email. And you can just go to our website, by the way. And our website, these webinars, the most recent ones are posted there, and the presentation, a link to that is posted there as well. So you got 2 ways of getting it. And then I see some links, I guess. Thank you, John Jones. Thank you, Mike. Yeah, okay. So Daryl, you were asking about the coefficients. Yeah, in PLS CAD for ADSS, if you use what I showed you, it will calculate the values. Excellent. Hey, Joe. Always glad to see you at these. Thanks for your positive feedback. In a distribution system, would you consider a critical crossing such as river, highway, a special consideration for SAG-10 calculation? I mean, when you frame the question that way, that would probably be a good idea, but would I consider it necessary? No, I would not. Well, but when you say critical crossing, I just said I would not use the simplified method for, say, over 600 feet. So if it's a critical crossing, you got a good chance that the distance is what's going to throw you into doing the ruling span concept type calculation. So, yeah. Thank you all for the positive feedback. Oh, that's a good idea, Joe. I see your comment. Suggest you show 4 or 5 transmission spans and the errors on the same slides as the distribution spans. That's not a bad idea. Yeah, I'll have to look at that to illustrate that when the spans are short, you get an acceptable error level. Remember, I showed there like a 1% difference between average and ruling span calculation. But really, that's not the whole story there. Average span in that context doesn't really mean anything. But I like the idea of contrasting the information or what you would get when the spans are short, like a distribution environment, and how it would be different. So I think what I would have to do is go run some PLS CAD calcs in a transmission span application and look at the error versus using the simplified method. So I do like that idea, Joe, and I will do that for a future version of this. Eventually, I'll get around to repeating this in our series. But thanks. Okay, any other questions? We're a few minutes past the hour. I'm happy to stay as long as people have questions. Okay. All right. Well, I'm not seeing any questions. Thank you for your time and attention today. Please do look for the follow-up email. Again, give us feedback, download the presentation, the slides, or the whole presentation itself, and then take the test if you're looking for continuing education credits. But thanks, everybody. I hope you have a great rest of the day and enjoy your upcoming weekend, and we'll see you next time. Bye-bye.
Good job, Mike.
Thank you.